My name's Bailey Lissington, and this is my smart farm system. It's a widely known fact that New Zealand's waterways are deteriorating, both from freshwater overuse and from soil leaching. The Canterbury region is one of the worst affected, with models from the Ministry of Environment depicting a bleak future for New Zealand's rivers and streams. This worsening issue has inspired me to pursue one possible solution, one which aims to mitigate both soil leaching and freshwater overuse. Soil leaching occurs when pores within a given volume of soil become filled with water from either rainwater or irrigation. The excess water begins to seep downwards into the groundwater, collecting the compounds within the soil, which wash downwards with the excess water content, contaminating the groundwater. By keeping the soil moisture content within the field capacity, which is a maximum amount of water that soil can contain before leaching occurs, and the optimum water content for plant growth, then the likelihood of soil leaching would be reduced. The smart farm system indicates to the farmer whenever it detects that the field capacity of the water is going to become exceeded, so the irrigation can be turned off, both reducing freshwater usage and soil leaching likelihood. Having a single soil moisture sensor around the farm would not provide accurate feedback, as it would only be representative of a small amount of land area relative to the large area that multiple irrigation systems would take up. The smart farm system connects up to 255 sensor modules, so the entire farm can be monitored in real time. Establishing this extensive wireless infrastructure solely for soil moisture monitoring seems wasteful, considering the capabilities of the technologies used. So many other variables relating to crop growth and soil health are also measured, including ultraviolet levels, soil pH, rainfall levels, soil temperature, air humidity, and air pressure. The bulk collection of these variables follow current big data trends, where predictions and relationships between the variables can become more accurate the more data that is collected, using current machine learning algorithms. The smart farm system consists of multiple sensor modules, which are custom designed circuit boards in a waterproof enclosure. The circuit boards contain the sensors for collecting the various variables, with a solar panel charging the batteries for 24/7 use. These sensor modules connect to a central data broker through a long-range radio interface known as LoRa, which reads the information from the various sensor modules and uploads it to a cloud server. This cloud server also receives local weather forecasts from Open Weather Map to determine whether rain is predicted to affect the soil moisture content. This cloud server also displays the collected data to the farmer through a web or app interface using Adafruit.io. This platform notifies the farmer whenever it detects that the soil moisture content will become exceeded, so that the user can turn the irrigation systems off to reduce soil leaching, freshwater overuse, and increase crop growth. The farmer can view these variables in real time, providing them with information regarding soil health and ambient conditions. I designed the smart farm system circuit boards in the program EasyEDA, which I ordered from JLC PCB, a supplier located in Shenzhen, China. The circuit boards were based on the schematic for the popular Arduino development boards, using the microchip technologies Atmega 328P microcontroller. The Arduino bootloader is flashed to the chips, allowing Arduino-based libraries to be used while programming the boards. The boards contain many useful features, including battery protection, multi-level relay networking, which enables the data from sensor modules to pass through adjacent modules, extending the range further than the 10 km rating of the LoRa modules, MQTT output, a standardized Internet of Things protocol which can be accessed by third-party services, and an accessible I2C interface for connecting additional sensors. Active pH measurement is traditionally difficult due to the redox reaction occurring between the metallic probes, in which the metal becomes oxidized, reducing the accuracy of measurement. A relay is utilized before the probe is connected to the microcontroller's analog to digital pin, blocking the continuity through the circuit and reducing the effect of oxidation while the sensor is not in use. One suggestion from professionals was to place the sensor modules on a pivot irrigator, directly measuring the effect of irrigation on the soil. This idea gave me the inspiration for designing a rack pinion setup for periodically lowering the soil probes into the ground, powered by a servo motor. In the future, I wish to add native interactions between the smart farm systems and current irrigation systems, so that the irrigation systems are controlled based on the likelihood of soil leaching, rather than relying on the farmer to turn them on and off. I also wish to develop a custom platform for data analysis and visualization, with an interface more suited for the target demographic. Thanks for watching.